open lecturer position, and this talk is a part of his interview today. Jack got his PhD from our department in 2016, working with Steve Thompson and Tim Schwartz. His bachelor's is in math from UBC Okanagan, and he also has a master's from UBC Okanagan. And he's currently a limited term lecturer in the department. Limited term means it's a one-year contract where he's sort of doing the things that we're hiring a lecturer to do permanently, just on a one-year basis. Jack has an interesting and diverse background in teaching and learning. He's taught numerous courses in the department, both previously as a sessional and through the course of his one-year limited term lectureship. But also he has TA'd numerous courses and served as a tutor marker for online courses. He was a research assistant for the Institute for the Study of Teaching and Learning in the Disciplines, and did work with various researchers or various educators who were looking to do educational studies. He has what I will call mad computing skills, and shares his experiences freely. So in a sense, doing one-on-one teaching all the time, and is also, by the way, graduate students is planning to be holding, and undergraduates for that matter, is planning to hold workshops over the summer on various computing topics that might be of interest. And I'll leave it to you to organize those with the graduate students as the time arises. He's working with the learning management system Top Hat to develop a course pack on statistical writing, and he has just in general an interest in experimentation in teaching, and has thought about, for example, playing soothing music during exams to help students with their test anxiety. So today Jack is going to give a lecture on linear regression aimed at a 302 or 305, in other words, a non-math audience. He'll give about a 30 to 40 minute talk, and then there will be time for questions at the end. Those questions can relate either to directly the material that he's doing, the presentation style, or other questions relating to teaching that you might like to ask Jack. So at this point, I'd like to welcome Jack and then turn it over to him.
Thank you. Not just soothing music. I was going to have the students pick it themselves and put it on these little $8 MP3 players that they can bring on their own. So if they want heavy metal, so be it. All right, so welcome back to class 302. This is where I'm going to make slight asides where I would have things. So this is where I would have like the agenda from last week and the agenda from this week, but it doesn't make sense in this context. Let's assume that we've just finished correlation. We've gone through a little bit of hypothesis testing at this point, and that you've had an introduction to R. So this would appear typically around the 4th week of the semester. So what we're going to talk about today, correlation and regression, and I'm going to be bringing up a heating cost example at the end of this. So, and as you can see, there's lots of space here for you to write because I did send out these notes to you earlier this week. And so if you have any other additional points you want to put on, that's where you would do it. So the big thing about regression is I like to think of it as very closely paired to correlation, except you get different things out of it. You get quite a bit out of it. It's mostly appropriate to describe a linear relationship between two variables. As the semester progresses, I'm assuming this is 302 where they'd spend a lot of time on regression. As the semester progresses, we'll be expanding this to more than two variables, nonlinear situations, and even binary responses. But for now, let's stick to the basics where it's just fitting a line to something and what can we do with that. So this is the magic formula here. Y equals alpha plus beta x plus epsilon. So there's a lot of fancy Greek letters for you, and as we discussed, when you've got a fancy Greek letter, it's a parameter. We use fancy Greek letters because only the Greek gods can truly know them. Us plebeians can estimate them though, and so we use plebeian, simple people letters for those instead, like A and B. So what do each of these mean? So alpha, that's going to be where the y variable is when x is 0. So what we're doing is we've got this response x, that we basically have as an input, and y, which are, response explanatory, x for explanatory variable that we put into it, and we've got response y that we get out of it. One thing that we have as a starting point, so to speak, is when x is 0. You can see that this, anything times 0 is 0. This on average is 0, and that's as far as we're going to go into it right now. That just leaves you with y equals alpha. This we would also call the y-intercept. You may remember from grade 10 or 11 math, at least in principles. Beta, that one is going to be probably the most interesting to us over the course of this. That's the slope. So that's the amount that the y variable changes when x increases by 1. Now, the notes I sent out to you earlier this week, you may notice that they don't say that. They say just a red underline there. So that would be your prompt to write this in as you had it. And then epsilon, which is just, I'm just going to leave that there as a placeholder for the error of the model. Because this won't predict things perfectly, because things often don't fit perfectly on a line. So epsilon is just there to show whatever we're missing or the residuals or leftovers. Also, if you have any questions along the way, because this is your classroom as well as mine, please feel free to wave your hand in the air, try and get my attention, and I will stop myself as soon as I can. Okay, so let's go into this a bit more. So just to write out what I was saying before, we've got x for explanatory. That's your what would you say that? A prompt to fill that in again. And then we've got y for the response as well. A and B, not A and B, fancy A and fancy B, alpha and beta. Those are our parameters, so they are describing the population. I'm not going to spit all over you with the again. With estimates that we would write as simply A and B, respectively. And then we've got this error term, epsilon, pronounced, or if you want to say it's the McDonald's arches that's fallen over, sign of our times, that it isn't a parameter that we're interested in estimating, because it's a different value for each observation. We'll cover more on this later. Also, for your own interest, you see I've got this optional reading afterwards on variable names, why we call it explanatory and response. So let's get into graphics. Graphics are fun. So I'll let you fill that in for a moment. Line of best fit. So we have here a set of dots. Not just any dots. These dots represent something. They represent two things, each one individually. How far it is to the right represents its x or explanatory value. How far it is to up or down, so here, that represents its response. So this circle here would represent something where we've got an x of about -1.5 and a y of about 3. This one up here would have an x of about -6 and a y of about 12. And you can see I've got about 40 of these here, and I am putting them into a line here, trying to describe them. So it's not describing every single point, but the general trend of them. And I have this here. Now that may look familiar because I've got the y equals a thing minus or plus another thing, x plus that error. Well, that's our regression equation again. So we'll go into each of those in detail there. So alpha, let's talk about that one first. Going back to this one here, that's 3.815, and you can see that when x is 0, this line is about 3.8, it's about 4. My hand is not perfectly steady, so I can't show you exactly. That's the intercept, and you can see that it intercepts the y-axis. Now, this always has a mathematical interpretation, that y-axis. That's something that's abstract. And sometimes, but not always, it has a real world practical interpretation as well, depending on what our explanatory variable is. Explanatory. So if it was heating costs, well, we just had a pretty nasty winter in which we had 0 Celsius a lot of the time. So if we were trying to predict heating costs as a response to the temperature outside, as it gets colder, naturally it costs more to heat your house. That temperature could be explanatory. That gives us an explanatory response of, or explanatory value of 0. That was the wrong button. All right. So it makes sense in that case, but it's not guaranteed to make sense. So another thing people do to predict these is they look at, another thing people use to predict, or to use linear models to predict, linear regression, is, say, fuel economy for vehicles. Heavier vehicles tend to get worse economy, or if you're going by fuel consumption, heavy vehicles tend to consume more fuel. So in that case, heaviness or mass, if our intercept would be 0 mass. So predict the fuel economy of a car that doesn't weigh anything. Doesn't make a whole lot of sense in that case. But we still have it in the model as a mathematical abstraction because it helps us make predictions. Where are we from here? Beta, on the other hand, I said this was of more interest to us, and that's because it almost always has a practical interpretation, at least for these regression examples when we're talking about real-world things. So beta, that's like a rise over run. It's our slope. You may have heard that term, slope is rise over run. It's how much y increases when x goes up by 1. So with the heating costs, as the temperature goes up by 1, what happens to the heating costs? Well, I mean the outside temperature. If it's getting warmer outside, it's going to cost you less to keep your home at a comfortable temperature. So we would expect it to be, that slope then to be negative. And again, it makes practical sense. It's how much savings you're making for every degree it increases outside. In the car case, well, now it does make sense. If we're looking at, say, fuel economy, if mass was our explanatory variable, then now you've got how much additional fuel costs is 1 kilogram going to cost you. And you can imagine as an engineer that that would be a really important thing to know. If I make these brakes heavier, how much is that going to cost me somewhere else? If I want to add like nice leather seats, how much is that going to bring up the costs of fuel economy, or the cost of fuel, things like that. So it does have a pretty good use to it there. It also has a way to estimate it based on these things we've already looked at. So we've got the slope here, beta, and that, because it is a fancy Greek letter, it's made of other fancy Greek letters because, you know, why would something so amazing be made out of something so mundane? We've got rho, that's the true correlation between two variables, that population 1 that we looked at last week. And then we've got sigma y over sigma x. And so sigma y, that's a general thing of like that measure of spread. So it's the measure of spread of the vertical variable, and then sigma x is the measure of spread of the horizontal variable. So what you've got here is sort of a scaling going on. Now, to estimate this, thankfully we've got something that looks very similar, but it's in letters that we can actually estimate something from. So we can get R. We can calculate it with, well, in R, using the core function. And we can estimate these using the SD function. We can get ourselves a slope. So don't be too off-put by all these Greek letters. It's not too big of an issue. We won't be dealing with the theory of them so much. We'll be dealing with the practicalities much more. So a few things I want to note about this slope. is that it's our link between correlation and regression. So correlation, remember, what were the highest and lowest values of correlation? Close. That's correlation squared. It's a little bit wider for correlation. Sorry, I didn't hear that. There you go. Good job. All right. So at -1 and 1, likewise rho is the same thing. So what sigma y over sigma x does is that scales it, because sigma y and sigma x, they can be anything that's positive. So that fraction can be anything that's positive. So that times that can literally be anything. So we can get a slope of anything. Now that's really useful because that means if we've got a positive correlation, we've got a positive slope. And that makes sense because what did correlation mean? As one thing goes up, the other goes up if it's positive. And if it's a negative correlation, as one thing goes up, the other goes down. And we would expect the same result from a slope as well. It's also impossible to have that less than 0 variability, so it's always going to be a positive multiplier. It's just the way that we scale it. And yeah, there it is in writing, and there's your prompt to write that. Beta, it's positive if and only if, so that means it's bidirectional. If and only if the correlation is positive. Beta is negative if and only if the correlation is negative. And now here's the really cool part. We can combine those two facts and say beta is 0 if and only if the correlation is 0. So you remember we had this nice simple t-table, or not t-table, yeah, this t-score formula for finding if the correlation was 0 or not with a hypothesis test. We can use that again now with the slope. So we can say, oh, if beta is significant, meaning different enough from 0, or rather its sample is different enough from 0 to tell us that the true value is non-zero, then that would only happen if the correlation was non-zero as well. And finally, if we've got a weak correlation, like that, a small number next to that multiplier, we would end up with something like this. We've got a lot of scatter around these points, and so the line of best fit doesn't do that great. It doesn't sort of follow that steepness here. If you've got a strong correlation, that line of best fit hangs pretty tightly to those data points, and it's sort of lifted up or influenced by it very well. So you ready to regress? Perhaps not that far, but far enough. Now, I've talked a lot. Are there any questions I can answer at this point? All right. If you do have any questions, I will be available after class, and you can ask them then, because I know it's a big audience, it's scary. I get it. All right. So, that regression equation, it gives you the slope, it gives you the intercept of that line that best describes y as a function of x. So x goes in, y comes out. If we have an x, we can get a y from it. So that means we can plug a value in and predict a certain value of y. And that can be really useful from previous data. Now we can predict the future. So, there's two different ways we can interpret that. Sorry. Let you fill those in for a moment. So what's the average value of y for a given x naught, where x naught is a specific value we're plugging in as opposed to the abstract x? Or what value would you expect for some new observation? We're going to get the same average value for them, but one of them has more uncertainty to them than the other, which we will look at in greater detail next hour. But let's estimate it first. So here's some R output. This is done with the LM function, which we'll be looking at again next hour, where we've got coefficients. So these estimates, that's our A and B. That's our estimates of alpha and beta. We've got intercept alpha. So this is again from heating costs. We've got 75 months of data here. So it's the average heating costs across months. And we're saying then that if x is 0, that's our y. That's our average y. So we don't know what it is, but we've got our best estimate that it would cost for a 0 degree month. It's going to cost you $29 to heat a given house. And then for every temperature degree it goes up in Celsius, it's going to cost, or you're going to save $1.83. So we can write that regression equation like this, where we've got y equals a plus bx. Now you're like, wait, hold on. You said plus. That's not a plus. Okay, so what's going on there is my beta value itself, I'm estimating it to be a negative number. So when I add a negative number, that's exactly the same as subtracting a positive number. So for the sake of writing it a little bit simpler, instead of saying plus negative 1.83, you'll see this very commonly, minus 1.83. Now, to make it less abstract, instead of x, I've written temp for temperature, and I've put error there, even though, again, this is a placeholder, and on average, it's 0. So this is our line of best fit in our scatter plot. So you can see, oh, that's a pretty strong correlation. And it should be. Outdoor temperature has a lot to do with how much it costs you to heat your home. It's like using one, you could probably predict the other pretty well. Each one of these blue dots, that represents a month. So this month over here, that would be, you can see this is clearly not from Vancouver because the mean temperatures only go up to 10. Welcome to Prince George. At about 10 degrees, how much is it going to cost to heat our house? Probably close to nothing. It's a well-insulated house. But if it's minus 15 out, you see we've got 4 months here where it was minus 15 as an average temperature. On those months, it cost about $50 to heat the home. And you can see that it just goes on a trend there. Now, what do you think would happen if it was 30 degrees out? Over here somewhere. How much would it cost to heat the home? Well, using this trend, it would cost like negative 25 bucks. So that doesn't happen. You don't get a rebate from BC Hydro because it's warm out. So that's an important point about these. So if I look outside of where the data is and I try to make predictions beyond what I've observed, not just new predictions, but new predictions that have explanatory values outside of the scope of what I'm studying in the first place, that's called extrapolating. You may have heard that term in other ones. I have a couple comics to show you about that later. Like if you weren't married yesterday, you got married today, you've got one wife. Extrapolating, that means you have 2 wives or spouses. And in a couple weeks, you'll have 30 spouses. Don't do that. Not the getting married every day. That I don't judge. I don't judge about marriage. But if you extrapolate, don't do that. I'll judge you for that. That's much worse. So don't take what you see here and try and predict here. Or consequently, try and predict out here. It may seem reasonable, but maybe there's something else that happens, some other phenomenon that you're not aware of that happens at minus 30. We don't know. We haven't measured it. We're not wizards. We just take data and describe it in simpler methods. So, what are some possible problems I could ask about this that would actually make sense? Let's look at minus 10. That's a reasonable thing to ask about. Asking about predicting a new month at minus 10, that's totally within our data. We would call that interpolating. Interpolating's fine. For that, we actually have some information to go by. So we could ask, what is the average heating cost of a house like this when it's minus 10 outside on average? Or what would it be for a single month if it's minus 10 on average? Now, those are two very similar questions with subtle differences, but they do come out to the same average. We just plug it in. Plug it in. Give you a moment to fill those in. So for temperature, we'll plug in minus 10. So we've got a negative times a negative here. So this will end up a positive in the end. Add 1830. And that's how we get this. That's why this number is higher than this number. So that's our cost. And you notice I've ignored the error at the end because that will have an expected value of 0. So if it's minus 10, let's say, November's coming up, I expect it to be minus 10. I can also expect that I would have to put away $48 to heat this home. Or if I'm working for the utility company, I can expect that much revenue. But there's a little bit of issue with that. I'm saying it's 48, but one, it's not a perfect line. I can't compute that exactly because, sometimes houses have a bit of a draft. Sometimes people have made upgrades. Sometimes people have their computers running more and that generates heat. So there's still sources of randomness. Also, so that's one source of randomness. Another source of randomness, which we're going to look at in detail here, is that what am I using for this? I'm not using alpha and beta. I can't get alpha and beta. I would love them. Instead, I have A and B. Poor me. Which means these are estimates, which means they have some measure of uncertainty to them, and that's what's in this red square here, the standard error. So that's a typical amount that these would be off by. We can use it for things like hypothesis testing, so you can see we've got our p-values here. P-values are wonderful this way, that they're very, very flexible within them. But it also means we can look at what else the slope and intercept could be and how that would affect our graph. So yeah, these are just estimates. So it's sort of the limitation of our plug-in equation that we could plug into something very similar. I've only got 75 data points. That seems like a lot, but it's not infinity. It's not a millions and millions of data points. So I don't know exactly where that line should be. It's only as good as the information we have. If I had more data points, this line, this standard error would be smaller, and this line would have more certainty to it, less uncertainty. So in reality, it could be any one of these lines. So I had one line before, and now I've got 10 different lines. You can see they converge near the middle, and that makes sense. Where I have the most information, I should have the least uncertainty. Near the end, they start to diverge, and at the upper end, they're starting to diverge again. Now, it looks okay like this, but let's kick it up a notch. Open with Chrome. So there you go. There's your wiggling dancing line. That this shows that that level of uncertainty. These are these same 10 estimates, except now you can kind of see it a little bit better, that we get more wiggle, more uncertainty at the ends where we have less information. And here, that line is pretty much staying solid. So what I'm really doing is I'm taking one of these lines. I don't know which one. What really it comes down to, what data did I happen to get that 75 months? And you can imagine that getting a lucky or unlucky break comes less likely when you're looking at, say, 300 months. And that's going to be a common motif. Sorry, did you have a question? Oh, okay. So I can send you the R code for this to generate it yourself. This is using an extension to R called animation, where if you tell it to build a plot 10 different times, instead of building 10 different plots, it builds it all as a single animation. So if you're interested in that, we have a department or a group here at SFU called the Vancouver Institute for Visual Analytics. They're in the Big Data Hub. You could actually talk to them about this and all sorts of other things, or you could come see me after class and I can show you sort of the wide world of visual analytics. But I'm glad you asked that. Thank you for your interest. Where else am I going with this? So I've got my uncertainty measure there, both as a static picture and as a wiggle dance. But the big thing there, and this is a common motif in statistics that I will say over and over, is that the more information we have, the less uncertainty we have. So as we would have gotten more and more data, if we had 300 data points instead of just 75, that line would wiggle a lot less. So it really could be any one of these. So if you're worried about this, that this is seeming like too confusing, that it's not just a plugin, that how do I deal with this uncertainty? Because uncertainty is scary. Don't be. This is going to be explained in the next week or so when we talk about prediction intervals and confidence intervals in a regression standpoint. So, you know, don't be like the great Patu here. Take it all in stride. So here's your optional reading in case you're interested. It's just a put on the end. Okay, so that's the end for today. I'll see you after class.
Recording this, we should probably use the microphone when we ask questions. So I will open up the audience for questions.
Thank you, Tom. I want to ask, when we do the regression, how many data points are enough we can do the regression?
How many data points? Well, technically, we only need 2, but you'll get a really, really bad measurement at that. More is always better. And we will talk about that next time when we talk about like standard errors, hypothesis testing. But really, I don't know, like I would say 10, but I don't want to just give you a number to latch onto and go 10, that's enough, because other problems arise and often they're solved by more data. Not always, but often.
Other questions?
Hi, I would like to know how did you get those 10 lines? Can you get 20 lines?
I could get 20 lines, yes. I could. So how I did that is I took that standard error and told R, okay, take the number I've estimated and give it a bit of variance, give it a bit of randomness or wiggle above or below what its current value is with that number. And I could tell it to do that as many times as I like. And again, if you're interested, I can also send you the R code and you can see how I did that. It's commented, it's got like a nice little build, do this thing 10 times. But you can change that to any number you wish and explore it on your own.
I had the same question. I was wondering which of those lines was the right one.
Technically we don't know. But the best estimate we have is the one we got from the linear model there. So that's why we're using that estimate as opposed to any of the others. That's
So
why
the other ones were just things you made up.
Yes, they are things I made up. They're just they're hypotheticals that if I had taken another 75 very similar measurements, those could have been the lines as well. Any other questions?
We got a talkative one over here.
That's fine.
Yes, I noticed in your output for the regression, there are 3 stars behind
Yes.
the things, the numbers. Wondering what these 3 stars means.
Okay. The 3 stars are a shortcut. If I were to take the whole output, now I cut it off so it would fit on the slide, it would actually tell you along the bottom what the 3 stars mean exactly. But when last week we were looking at hypothesis, or not last week, it would have been week 2, we were looking at hypothesis testing, and I talked about p-values, how smaller p-values mean stronger evidence against some null, whatever that null is. People like to say the null hypothesis is the dull hypothesis. It's the most boring one. In this case, the most boring one for slope would be that there is no slope, or there's no trend between them. So these stars, so first this number here, even though it looks like a bunch of letters and garbage, what that means is that p-value is less than 15 zeros and then a 2. And that's very, very small. And these 3 stars here are just a shortcut for you, so you don't have to interpret the numbers directly, saying, yeah, that p-value is very small. If I want to be exact, it means it's less than 1 in 1,000. So you can imagine, and we will run into this later, if you had a ton of different numbers here, you wouldn't want to read all the numbers. You'd want to be able to really quickly find which things are significant. And then you would say, oh, look for the ones that have stars. The more stars, the more significant. 3 stars is the highest level of significance. Does that clarify things? Okay, thank you.
So I noticed when you presented the model, you had this Greek epsilon thing. So you're saying this model isn't quite right. There's something wrong with it. So are those errors? Is that the error with my model? Or like, how do I know how much my model is off? Like, how do I know if this model is good or not?
Oh, I'm glad you asked that one. Okay, so there's an old saying by George Box, very famous statistician. All models are wrong. Some are useful. That's what this comes into, is if you look at the data here, we have data points that are scattered around the line. And so what that means is I'm not predicting perfectly. I can't, with a formula so simple, or with just a line, predict what each individual one is. So like I would predict exactly on the line for, say, -6 degrees, but you can see that my heating costs for that particular month would be a little less. Well, why didn't I make the line lower there? Because I also have ones above that particular heating the higher heating cost for that particular temperature. So the line just does its best to fit that data, whereas there's a lot else going on. Now, rather than try and handle every single little thing, and there are very advanced statistical methods that handle a lot more things, but we're going to start with what's called a model, and a simple one at that. A model being just like a simpler representation of what's true. So yeah, it is wrong. All of these things have a little bit of error, and the idea is to try and get those errors small enough that we're not particularly concerned about them, that what information we are getting out of it is at least useful, that we get most of the usefulness out of it, and then leave all of these random happenstances, these leftovers, these residuals, so to speak, behind. And those residuals are those errors, and like, how do we know it's good enough, things like that. We will look at that when we get to diagnostics in week 6, where we will look at the residuals, the leftovers, and see if we've got some plots and some statistics to use to see what is quote unquote good enough.
If I were to draw visually my line of best fit or draw one, and you were to draw one, or you take any of those 10 that you showed before, they all look pretty good. And you said, but the red one, the one in the table, was the best one. Why is that one better than all the other ones?
Okay, so thank you for asking. That comes right back to that previous question about those errors, about those residuals. that this is also called the least squares line. And what that means is the errors, the amount that each dot is off from its predicted value on the line, this is the one line that is mathematically proven to have the smallest squared error amongst all of these added together. So if I were to just fit by eye, the one I would get would have a squared error that was larger. Now, why we would care about squared errors and not, say, other errors, that's actually a point of contention and why there's modern regression methods in, say, Tom Logan's course that could give you an alternative to that. But this one is one of the most mathematically useful to work with, as in it's the simplest. And because it's squared, that means errors below and errors above count for the same, because a negative times a negative is a positive. Does that clarify things? Okay, great. Any other questions I can answer? I think this is constructive, by the way. I mean, I know I'm not showing slides, but I think we're all learning a lot as a group.
Sorry. This will be my last question. I would like to know, do you have formulas to calculate A and B? Do we need to know those formula, or we just plug in the data to the software to get those numbers?
For this course, all we'll be doing is plugging in the data. I did show you a formula early on, but I'm not too worried about you memorizing this or the one we use to predict it. The only reason I'm sort of showing you that is to kind of give you a character of what's going on, or give you an idea of like that these are connected to correlation, which we looked at in week 3. But no, for this course, it's much more preferable to go from this information here, what the computer would give you, because for formulas, well, nowadays that's largely the computer's job to do the formulas. And what a human has to do, or what only a human can do, is make sense of that data. So in your course, and because 302 is largely life sciences and health sciences, you'll be given data, say from a hospital or something, and you say you have to write a report or make some sense out of it. And from that data, you'll be able to get output like this. And so you don't need to do heavy mathematics with it, but what you do need to know is, are these numbers, what are they telling me, and can I believe it? Like, have I done the appropriate steps in order to find it? So because I think that that's a good simulation of, or a good representation of what at least people in health sciences in industry are looking for right now, that's how I'm hoping to structure this course as well.
If this is a course for science student, I want to know how to estimate the alpha and beta. Can you give me the mathematical expression? Okay, you already given us, but I want to know the idea how to derive the formula there.
Okay. So first, this would be this sort of thing would be better suited for a statistics major track course, because this is a service course. But if you are interested in it, and I think it's very admirable for science majors to take this service course. That's how I started. I can give you the derivations. I can give you the notes I have for that course as well, for your interest. But it won't be on the exam. So you can know it, but I'm not going to force you to know it.
How to derive idea? How to derive the formula there?
Okay. Yeah, I mean, like, I can show you my notes on that, specifically like the least squares equation, x transpose x inverse x transpose y. I've got some notes on that I can show you immediately after class. Jigwa? Oh, sorry.
So I understand when you do this model, all models are wrong, but some models are useful. So all models are based on some assumptions. So can you tell me, when you do this linear regression model, what's the assumption you make for this model?
Okay, I can give you a little bit of information on this now, but we are going to talk about this at length in week 6 when we get to the diagnostics and assumptions from there. So first, what I'm assuming is, now if I go back to, we can actually see some of this from the formula we've got here. So when we deal with correlations, we had this assumption that both X and Y individually followed a normal distribution, and that there was some fixed correlation between them. So that's part of what we're assuming. We're also assuming that there are no, that there's no non-linear trends between these, and we're assuming that X and Y have been measured perfectly well. What we're going to be looking at is things like Cook's distance. I'm going to be looking at influence from that, and we'll be doing things like looking at those residuals to identify outliers, things like that, to see how reasonable are these assumptions, because they're never perfectly right, especially with a limited data set. But a more important question for whether or not the results we get from them are meaningful is, are they right enough? That clarify things? Okay, thank you. Questions?
Question, I think it's on the slide 50 or 40 on the regression equation. Next one. The regression equation, the one has this one. For the interceptor here, I just wonder what here is the 29.28 and why not 29.29? The equation, the right one.
Oh, you know what? You've caught me in a mistake. You're absolutely right. That should be 29.29. I should have rounded that up, and I have no other recourse other than to, yes, admit it should be 29.29. Okay, thank you.
By the way, you get a donut as a prize when you leave. Anyone else find any mistakes they want donuts for? There are donuts, and if you find a mistake, you get one. Are there any other questions? Okay. You just want the donut. That's why the hand was up.
That's fine. Yeah,
Fair enough. Okay, thank you, Jack. I want to say that we will see this with all of our candidates. It's a tricky balance that you have to play between knowing that your audience is a lot more advanced than what you'd normally be giving this lecture to, and trying to play the role of an instructor for students who are still trying to understand this, yet knowing full well that everybody here is able to understand fully and critique every last thing you say. And Carrie's question, do you know how to derive that? Well, yeah, okay. Do we want to see a derivation now to prove that you know it, or do we want to, or is that what you would do with a precocious student? And I see that you chose to stay in character and say, that's a great question. Come talk to me later, because it's not something I want to test on. And that's interesting. By the way, ask him later if he does know the derivation. Let's find this out. Yeah, right. The idea. Yeah.
Oh, I thought it was a great question and challenging, but really good.
Okay, well let's thank Jack once again, and thank you all.
Thank you. Okay.